we're going to be beginning topic 6.9, integration by using substitution. Make sure you write your last name and your first name up at the top of the page. And you can pause to write your essential question, your I can statements. So the essential question is, how do you use U substitution to integrate? And our I can statements are, I can integrate an indefinite integral using U substitution. I can integrate an inverse trigonometric function. I can integrate using U substitution with the change of variable method. And I can integrate an indefinite integral using U substitution. So U substitution is very similar to the chain rule. So you have to remember that the chain rule tells us that we have, if y equals the antiderivative of u, and u equals g of x, then the derivative of f of g of x is the derivative of f of g of x times the derivative of the inside. So remember, we used to say that this one was orange, and then we take the derivative of it. So it's the derivative of the outside times the derivative of the inside. So from the definition of antiderivative, it follows that when I take the derivative of the inside composed with the, derivative of the outside composed with the inside times the derivative of the inside, that when I integrate that, I get f of g of x plus c, or f of u plus c. So basically what's happening is, you'll notice that to recognize this, I have to have the derivative of the inner function. When I integrate that back, I get back to the original function just composed with the inside function. It might be easier to think of it as f of u times du dx times dx, or f of u plus c. All right, so let's see if we can recognize this pattern. So I'm going to start by looking for my u's, and u is typically inside the function. So I see a u right here. So I'm going to say that u equals x squared plus 1. Then I'm going to take its derivative. So du equals 2x, and I notice that the derivative is here, dx. In this case, it looks like I can just substitute in. So I have the integral of u to the fourth, and then my du is being substituted in for the 2x dx du. And I'm going to go ahead and just integrate that. So I get u to the fifth divided by 5 plus c. And then I substitute my u value back in. So I have x squared plus 1 to the fifth divided by 5 plus c. All right, so I'm going to look for my u again. I'm going to use x cubed plus 1. And then I'm going to take its derivative. So du equals 3x squared, which dx, which happens to also be in there. Okay, so we're going to go ahead and substitute in now. So I've got the square root of u, and then for the 3x squared dx, I have du. I'm ready to integrate. I'm going to convert this to the 1/2 power. And when I integrate to the 1/2 power, I get u to the 3/2 divided by 3/2, or multiplied by 2/3, plus c. And then I'm going to resubstitute that u back in. So x cubed plus 1 to the 3/2 plus c. All right, I'm going to look for my u again. It looks like my u is, I'm going to do this to the side, sorry. Looks like my u is the tangent of x plus 3. That means du, when I take the derivative tangent, I know I get secant squared x dx. And I notice the secant squared x dx is also in there. So I'm going to go ahead and substitute in. So the integral of the u for the tangent x plus 3x, and du is going in for secant squared x dx. When I integrate that, I get u, I'm going to add 1, so to the second divided by 2 plus c. So that means I'm going to substitute my u back in, tangent of x plus 3 squared over 2 plus c.